you will be able to learn a new family of distribution named ChiSquare distribution. You would also know about the properties of ChiSquare distribution and how this distribution is different from the other commonly used distributions. We shall also learn 4 main applications of ChiSquare distribution. The first 2 concerns the population variance, namely how to construct a confidence interval for the population variance and standard deviation. Also, how to test a hypothesis for the population variance. The other 2 applications are related to hypothesis testing for the chi-square test of goodness of fate and the chi-square test of independence of attributes, which are covered in the chi-square distribution module. So, the mean and variance are the 2 parameters that hold great importance to understand any distribution. I am sure you know that mean is a measure of central value, which is a summary measure of any distribution, and variance is a measure of spread of observation around any central value. The inferential statistics extensively concerns with both these measures for hypothesis testing as well as estimation. We have learned in our earlier modules that how statistical inferences involving population means and proportions can be done. Now, when our interest centers on the inferences about population variance or standard deviation, we introduce 2 new distributions, namely the chi-square distribution and the F distribution. The former, which is chi-square distribution, is used to make interval estimates and hypothesis tests about the variance of a single population, and the latter, F test, is used for inferences about variances of 2 populations, which we have covered in our earlier modules. So in this module, we will learn in detail the chi-square distribution. For example, manufacturers often face the situations in which they are required to show that their products adhere to the requisite specifications. For such purposes, chi-square is applied whenever it is a case of one sample. Define chi-square distribution. Now, we have learned in detail that sample mean is used as a basis for making inferences about the population mean. In the similar manner, the sample variance has a key role to play for making inferences about the population variance. We have studied in our previous module that the sample variance S square is an unbiased point estimator of the population variance sigma square. And if you recall, it is defined by the formula where we say S square is equal to sigma xi minus x bar square divided by n minus 1, where the summation is over I, and we have the small n is the sample size and x bar in this formula is the sample mean. Now, this S square formula could be denoted as our first equation. So suppose now x1, x2, x3, xn be a random sample of size n drawn from a normally distributed population with the characteristic mean mu and standard deviation sigma. So if we multiply both the sides of the equation 1 with n minus 1 upon sigma square, then you can see it can be rewritten as n minus 1 upon sigma square into S square is equal to sigma xi minus x bar square upon n minus 1 into n minus 1 upon sigma square. So if you simplify this, on the left hand side we have n minus 1 s square upon sigma square, and right hand side simplifies to sigma xi minus x bar square upon sigma square. Let me denote this as second equation. Then you will find that the random variable n minus 1 into s square upon sigma square has a chi-squared probability distribution with n minus 1 degrees of freedom. In notational form, we can write this as n minus 1 into s square upon sigma square distributed as chi-square nu, where you know that degrees of freedom is denoted as nu equal to n minus 1. It is denoted as chi-square, where chi is a Greek letter, and I am sure you know it can be pronounced as chi. Properties of this chi-square distribution. The chi-square distribution is basically a continuous probability distribution. The chi-square distribution has only one parameter, which is its degree of freedom or degrees of freedom. Now, similar to t-distribution, we use chi-square nu notation to suggest that the distribution is always defined for a given value of degrees of freedom, and as the value of degree of freedom nu changes, the shape of the distribution would also change. The possible values that nu can take are from 1, 2, 3, etc. Now, unlike z and t distributions, chi-square distribution is not a symmetric curve. Let me repeat. Unlike z, which is a normal distribution, and t distributions, chi-square distribution is not a symmetric curve. Rather, it is a positively skewed curve and has a tail to its right side. As degree of freedom increases, you can see from the diagram below, the distribution becomes less and less skewed and moves towards symmetry and is approximated by the normal distribution curve. In particular, for nu, which is degrees of freedom greater than 40, the chi-square distribution approaches a normal distribution. The chi-square distribution is also related to the standard normal distribution, in fact. So we have learned in our earlier module that if x is distributed normally with mean mu and variance sigma square, then z is equal to x minus mu upon sigma has a standard normal distribution. Now we can show that z square is not distributed normally, rather it has a chi-square distribution with 1 degree of freedom. Further, to generalize, if z1, z2, z3, zn are n independent standard normal distributions, then the sum of their squares, which means sigma zi square, where I is from 1 to n, which is nothing but I am sure you can make out is z1 square plus z2 square up to zn square, will be equal to sigma I from 1 to n, where we have the summation of xi minus mu square upon sigma square, and it has the chi-square distribution with n degrees of freedom. However, in using sample data, deviations are computed from x bar in place of unknown population mean mu, because the population mean mu may not be known to us. Now, this in turn results in loss of 1 degrees of freedom to estimate x bar. Therefore, the statistic can be written as sigma xi minus x bar square upon sigma square, and it will be now distributed as chi-square but with n minus 1 degrees of freedom. Further, if we work on the statistic sigma xi minus x bar square upon sigma square, we can easily show that this summation is nothing but is equal to n minus 1 s square upon sigma square, as we did try to put it earlier. The right-hand side term, therefore, as already defined in our equation 2, has a chi-squared probability distribution with n minus 1 degrees of freedom. So by construction, we see that the chi-square distribution can take only non-negative values, because it is a sum of the squares of the z random variables, therefore must always be positive. Also, you can see in equation 2, it is equal to n minus 1 into s square upon sigma square, and all quantities here are non-negative, whether it is s square or sigma square or n, all are non-negative. The minimum value it can take is 0, and it can go up to any value on the positive side of the distribution. The mean of chi-square nu, or with new degrees of distribution, is equal to the number of degrees of freedom. That is, mu is equal to nu, and its variance is 2 multiplied by the numbers of the degrees of freedom, which means that sigma square is equal to 2 nu. Let me emphasize, nu is the degree of freedom. Therefore, we can write that as this degree of freedom, or nu, tends to be infinity, chi-square nu will tend to be distributed normally with mean nu and variance 2 nu. It must be therefore kept in mind that the chi-squared probability distribution is used when the samples are chosen from a normally distributed population. Interpret the degrees of freedom. The term degrees of freedom in general means the number of observations that can be freely or independently determined in any sample. Here, the chi-square statistics is based on sample variance, which in turn requires some of the square deviations calculated from the sample mean. That is, I'm sure you know, means nothing but sigma I xi minus x bar square. So at first sight, we might think as if it is n. However, the sample mean has an important property that some of the deviations of the sample observations from the sample mean is always 0, which means I am sure you know that sigma xi minus x bar is equal to 0. Now, on account of this, in any sample, all the n observations cannot be freely chosen. The investigator can choose only n minus 1 observations independently. The nth observation should be such that the constant as specified earlier, which is sigma xi minus x bar over I, and is equal to sigma xi minus nx bar equal to 0, is satisfied. It is to be noted here that if mu were known, all the n observations to compute sigma xi minus mu square could be independently determined. However, the population parameter mu is rarely known. This is the reason, while calculating sample variance, the divisor in the formula s square is equal to sigma xi minus x bar square upon n minus 1, and is n minus 1 and not n. So let me emphasize, the divisor in the formula s square is n minus 1 and not n. Determine the area under the chi-square density curve and find out the chi-square critical values. The chi-square is tabulated in our table A.5, which is attached at the end of this module. You can refer to that table later on. The body of the table gives critical values of chi-square for a given value of the degrees of freedom and a specified area to the right side of the chi-square density curve, which is nothing but your alpha. The first column in the table gives degrees of freedom, or df, for all its values, or the degrees of freedom for all its values starting from 1 up to 40. The first row gives 10 specified areas of alpha covered to the right side of the density curve. For example, the value of chi-square given at the intersection of row corresponding to nu equal to 10 and column corresponding alpha equal to 0.05 is 18.307. This implies that for a chi-square density curve with degrees of freedom equal to 10, the area to the right of the value is equal to 18.307. On the horizontal axis is 5%. The notation used for this is chi-square 0.05, 10. It means the probability chi-square 10 is greater than or equal to 18.307 is 0.05. This is also depicted in our figure 2. You can see it more clearly from there. Now, this can also be interpreted as the probability of obtaining a value of the test statistic chi-square 10 with degrees of freedom 10 equal to or greater than 18.307 is 5%. Now this also meant that area to the left of 18.307 is 95%, which can be written as that probability chi-square 10 less than or equal to 18.307 is equal to 1 minus 0.05 is equal to 0.95. So in general, chi-square alpha nu, called a critical value of the chi-square distribution, gives a value measured on the horizontal axis of the chi-square density curve with new degrees of freedom that captures alpha area to the right side of the curve. So if you look at the diagram, you can see that the shaded area, which is the tail area, is equal to alpha and is the critical area, which is also known as the region of rejection. Further, since the chi-square distribution is not symmetric, both the left end tail as well as the right end tail cuts off areas to be tabulated. Now, suppose we require a critical value of the chi-square nu distribution such that alpha areas falls to the left side of the distribution, which means we want, let's say alpha is 5% and we want 5% area in the left side of the distribution. Now this can be interpreted as 1 minus alpha percent area to the right side. Therefore, we write this as chi-square 1 minus alpha comma nu. So for example, to find a critical value of chi-square 10 density curve such that 5% area falls to the left side of the chi-square 10 density curve, we need to find chi-square 1 minus 0.05 comma 10, which is chi-square 0.95 comma 10, or which can be interpreted as chi-square degrees of freedom with 10 and 95% critical area. Now this you can see is equal to 3.940, which is the value at the intersection of the row corresponding to nu equal to 10, column corresponding to alpha is equal to 0.95. Now in terms of probability, this means that probability that chi-square 10 is greater than 3.940 is equal to 0.95, or we can also write it as probability chi-square 10 is less than or equal to 3.940 is equal to 0.05. Additionally, we can also say that probability 3.940 less than or equal to chi-square less than or equal to 18.307 is equal to 1 minus 0.05, which is your left-tailed cutoff area, plus 0.05, which is our right-tailed cutoff area, and hence is equal to 1 minus 0.10 is equal to 0.90. That means that for a chi-square 10 density curve, area captured between the values 3.940 and 18.307 measured on the horizontal axis is 90%. In notation form, we can write this as probability chi-square 0.9510 less than chi-square 10 is less than or equal to chi-square 0.5 comma 10 is equal to 0.90. Determine the values of the following quantities. First, for A, chi-square 0.05 comma 18, which means find out the value of chi-square for 18 degrees of freedom at 5% level of significance. B, chi-square 0.01 comma 20, C, chi-square 0.005 comma 25, and D, chi-square 0.99 for degrees of freedom 28. Let's find out the solution of all these four parts. So using table A.5, we can find that chi-square chi-square at 0.05 and 18 degrees of freedom, which is our part A, is equal to 28.869. How do we get this? This is the value at the intersection of row with degrees of freedom nu equal to 18 and column corresponding to alpha equal to 0.05. Solution of part B is you can find out the value at the intersection of row with nu equal to 20 and column corresponding to alpha equal to 0.01, and we get this value of chi-square 0.01 comma 20 equal to 37.566. Similarly, for the third part, we can see that the value at the intersection of row with nu equal to 25 and column corresponding to alpha equal to 0.005 gives us the value of chi-square 0.005 comma 25 equal to 46.928. Similarly, you can see that the value at the intersection of row with nu equal to 28 and column corresponding to alpha equal to 0.99 gives us the value of chi-square 0.99 comma 28 equal to 13.565. Let us take another example and find out the following probabilities. The first part is that probability of chi-square for degrees of 28 or degrees of freedom 28 less than 13.565, or chi-square 28 greater than equal to 41.337. The second part could be where probability of chi-square 16 degrees of freedom is greater than or equal to 6.908 but is less than or equal to 28.845. So how do we find the solution? Again, using table A.5 from the row corresponding to degrees of freedom 28, we find that chi-square 28 is equal to 13.565 for alpha equal to 0.99, and for area to the left of chi-square 0.99 and 28, it comes out to be 0.01. And chi-square 28 is equal to 41.337, which appears corresponding to column alpha equal to 0.05, which is area to the right of chi-square 0.0528. Therefore, the required probability of 13.565 between these two intervals is equal to 0.01 plus 0.05 and is equal to 0.06. For part B, we can again look at table A.5 and we see that corresponding to nu equal to 16, the value 6.908 appears for alpha equal to 0.975 and the value 28.845 appears for alpha equal to 0.025. Therefore, using our earlier notation, we find that the required probability is equal to 1 minus 0.025 plus 0.025 and hence comes out to be 0.95, the percentiles of the chi-square distribution. As we know, chi-square 0.5, 10 is interpreted as a value on the horizontal axis of chi-square density curve below which 95% of the observations fall and the rest 5% lie above it. Therefore, it can also be defined as the 95th percentile of the chi-square 10 distribution. Chi-square 10 means chi-square for 10 degrees of freedom distribution. Similarly, chi-square 0.95, 10 gives 5 or 5th percentile value of the chi-square 10 distribution. In general, we can say if alpha by 2 area falls to both the sides of the distribution, then under a chi-square nu distribution curve, then the two critical values to the left and right side are given by chi-square 1 minus alpha by 2 nu and chi-square alpha by 2 nu respectively. And the area captured between these two values is equal to 1 minus alpha by 2 plus alpha by 2, which is equal to 1 minus alpha, which can be seen in our figure 3. and we can denote this as probability of chi-square 1 minus alpha by 2 comma nu less than chi-square nu less than chi-square alpha by 2 nu equal to 1 minus alpha, and this could be our third equation. So if you look at this figure 3, we have the middle area, and which is equal to 1 minus alpha. We have alpha by 2 in the upper tail, and we have now alpha by 2 in the lower tail. Similarly, you can have example 3 where you can find out the 99th percentile of the chi-square distribution with the degrees of freedom 36, or the 10th percentile of the chi-square distribution with degrees of freedom as 22. We have provided this solution in the text. You can refer to that or do it as an exercise for yourself. The applications of this chi-square distribution, that where do we use this chi-square distribution and what is the importance of this chi-square distribution in terms of applications. The two important applications of the chi-square distribution are concerning population variance and standard deviation. Firstly, we will learn to find the confidence interval estimates for the population variance sigma square and standard deviation sigma. And then we would learn about the hypothesis testing for the population variance. Confidence interval estimates for the population variance sigma square. As we know, variance provides valuable information concerning the spread of the distribution around a central value. That is, it tells whether the distribution is symmetrical or skewed. However, the population parameter sigma square is rarely known. Therefore, as said earlier, we try to estimate it. And this estimation could be an unbiased estimator of sigma square. But it being a single number conveys no information on the precision and reliability of the estimate. Therefore, through confidence interval estimate, we provide an interval of plausible values within which the given parameter is expected to lie for a specific confidence level. Using chi-square distribution, we obtain the confidence interval estimates of the population variance sigma square from a random sample drawn from a normally distributed population. Suppose we require 100 into 1 minus alpha percentage confidence interval. An interval has a lower endpoint and an upper endpoint. That is why it is an interval. This would mean we have alpha by 2 area on both the left and the right tail of the distribution. Now then the two critical values of chi-square density curve on the left and right side are given by chi-square 1 minus alpha by 2 comma nu, which is also read as chi-square as nu degrees of freedom and 1 minus alpha by 2 critical reason. And the second is chi-square alpha by 2 nu respectively. So using equation 3 above, we know the area captured between these two critical values is equal to 1 minus alpha. From equation 2, you can make out that using the definition of chi-square random variable being equal to n minus 1 s square upon sigma square, where nu is n minus 1, and replacing it in place of chi-square nu in the equation 3, we obtain a simplified version, which is that probability n minus 1 into s square upon sigma square is greater than chi-square 1 minus alpha by 2 nu, and chi-square alpha by 2 nu is equal to 1 minus alpha, and this we can describe as our equation 4. Now manipulating this inequality inside the parenthesis in 4 such that sigma square remains in the middle, we obtain probability P equal to sigma square greater than n minus 1 s square upon chi-square alpha by 2 nu and less than n minus 1 s square divided by chi-square 1 minus alpha by 2 nu. And this probability is equal to 1 minus alpha. This is our equation 5. So the equation 5 gives a 100 into 1 minus alpha percentage confidence interval for the variance of a normal population. In this equation, if we put the value of sample variance S square, which is computed from the given sample observation, we obtain n minus 1 into S square upon chi square alpha by 2 nu and n minus 1 S square upon chi square 1 minus alpha by 2 nu, defined as the lower and upper endpoints or limits of the confidence interval respectively. The square roots of both these limits would give a confidence interval for the standard deviation sigma. It must be kept in mind that this is a random interval as it involves a random variable S square whose value changes from sample to sample. Example 3 or another example, this is where a sample of size 20 drawn from a normal population gives S square is equal to 14,440. Obtain a 95% confidence interval for the variance sigma square and a standard deviation sigma of this population. So you have this solution which you can see on your screen. We have 1 minus alpha equal to 0.95 and alpha equal to 0.05. Therefore, alpha by 2 is equal to 0.025 and 1 minus 0.025 becomes equal to 0.975. And degrees of freedom nu in this case is 20 minus 1, which is equal to 19. The two critical values of chi-square distribution for the areas of 1 minus alpha by 2 and alpha by 2 for this 19 degrees of freedom are equal to 8.906 and 32.852. So the lower and upper limits of the confidence interval for the variance sigma square are equal to n minus 1 S square upon chi square alpha by 2 into nu, which is on substitution of the values is equal to 19 into 14,440 upon 32.852 and comes out to be 8351.4. And similarly, the upper tail value on substitution of the values gives us value equal to 30,806.2. If you take the square root of each of these limits, you will get the limits for sigma, and these comes out to be 91.39 and 175.52, which are therefore the 95% confidence interval for standard deviation sigma. The hypothesis testing for the population variance sigma square. There are many reasons why knowledge of the population variance holds an important place in understanding any random phenomena. For example, a pharmacist who has to meet a particular specification regarding the potency of a medicine would certainly like to know whether the variability in the potency of a medicine is within the acceptable limits. Similarly, a teacher experimenting on different teaching methods would like to know whether the variability in the marks of her students has remained the same or it has declined. On the basis of the sample observations, testing hypothesis about the value of the population variance sigma square is one of the most significant applications of the chi-square distribution. So let us explain the procedure. Let x1, x2, x3, xn be a sample from a normal population with both the parameters mu and sigma square unknown. And we wish to test that the hypothesis that whether the population variance is equal to some specific value, say sigma 0 square. That is our null hypothesis H naught, and alternative hypothesis HA could be written as H naught equal to sigma square equal to sigma 0 square, and H naught A we can write down sigma square not equal to sigma 0 square. To test this, we use the test statistics, which is n minus 1 into S square upon sigma square in equation 2, which has a chi-square distribution with n minus 1 degrees of freedom. In other words, I can also say we can write this as n minus 1 into s square upon sigma square distributed as chi-square nu, where nu is n minus 1. Now, we can simplify this, and if you substitute the value of sigma square equal to sigma 0 square or sigma naught square under the null hypothesis, then the test statistics becomes equal to n minus 1 into s square upon sigma 0 square. Now, the quantities n minus 1 and s square are calculated using the sample data. So, given the level of significance alpha, the two critical values of chi-square density curve could be calculated as chi-square 1 minus alpha by 2 for degrees of freedom nu and chi-square alpha by 2 for degrees of freedom nu. Now, if the calculated test statistic lies within these two limits, we fail to reject the null hypothesis. And if it is equal to or lies beyond these two limits in either of the direction, null hypothesis is rejected, which is similar to our earlier examples of t-test, etc. The non-rejection and rejection ranges are therefore given by our formulas, which I don't want to repeat again and again, and I'm sure you understand that we do not reject the hypothesis if it is within the range, and we reject if hypothesis H0 in favor of H1 if it is outside the range. Check the assumption of normality regarding chi-square test. In our earlier modules, we learned that many distributions such as TEF distributions are based on the theoretical requirement that the population sampled must be normally distributed. Similarly, the chi-square test on a single population variance, which is sigma 0 square, is also very sensitive to the assumption of normality. On account of chi-square test's non-robustness to the assumption of normality, the computed chi-square statistics may noticeably differ from the actual test statistic if the sample population is not normal. We may even get contrary results due to the violation of this assumption. Thus, the investigator needs to be following cautious approach in using this test. We have some examples. We have introduced these in our module, and I would refer to them as an exercise of this example 4, and we have also provided the solution to these in your module, and you can learn from these examples how do we ultimately apply this test. This module explains in detail the properties and applications of an important form of distribution termed as chi-square distribution. It is a continuous distribution, it is positively skewed, and has degrees of freedom as its single parameter. However, it tends to normality as the degree of freedom increases. We have also learned that it is defined as a ratio of positive numbers. Therefore, it can take only non-negative values on the horizontal axis of its density curve. Hence, we can say that chi-squared probability distribution curve starts at the origin. We have also learned that its main applications concerns population variance or standard deviation, and when a sample is taken from a normal population, inferences regarding interval estimation and hypothesis testing of population variance are illustrated using chi-square distribution.